Hi guys, do you hear me?
Hello, yes.
Yeah, okay, well, good. So do you have any questions for today? Mm, any topic to discuss?
No. We're gonna discuss today self-attention, right? Like we're gonna be yeah.
Yeah, self-attention and transformer architecture.
Mm-hmm. Yep. Okay.
Uh, yeah, okay, I will send you link to the test in the beginning of our lesson. I will send you this link in the chat. So let me know, do you have access to this link? Yes, we probably do. Okay, fine. So you have around, I don't know, around 6 minutes to complete Google form as always. And then we will discuss all the options in all the questions. And maybe you will have extra questions.
Are you sure we have the right Google form? I feel like it's the same that we had last time.
Yes, indeed. I agree.
No, there are a few questions different. Yeah, and you had similar questions in previous one, but we will repeat some questions. But
Okay, okay.
hmm?
Okay, okay, yeah, I see there is min max something something. So yeah, we didn't have that last time. Okay.
Have you finished yet?
No, not yet.
Okay, let me know, please, when you will be ready for discuss all the questions.
I finished.
Okay, anybody else?
Yeah, me too.
Great. Okay, I will share the screen and then we'll just go in through all the questions. I hope we will finish earlier today because I feel that we have not really long notebook with code, and maybe we will hurry up and discuss all the questions. So in the first question, we will discuss attention mechanism in sequence to sequence. It's a little bit grammar rule. Not good. Okay, so the first question is the first option. Sorry, it's incorrect because actually attention introduce additional computation because they compute attention scores between tokens. This requires more operations, not fewer. The second one is correct because the attention mechanism computes scores between all pairs of token and resulting in a complexity squared n, where n is the sequence length. This increases the computational cost compared to models without attention. And the last one is incorrect because, as mentioned, attention increases computational costs by introducing additional steps for score and token interactions. So the second question, the correct answer is the last option. The first one is incorrect because in a encoder-decoder architecture typically doesn't interfere with the encoder while it's processing the input. Instead, it's supplied later when the decoder generates the output. The second one incorrect because attention is not applied after the decoder has processed the entire output sequence. It's applied during the generation of each token in the output sequence. And the last question, we can say that the attention mechanism, last option, attention mechanism is used in the decoder while it is generating each output token. It computes attention scores based on the encoder's output and helps the decoder focus on relevant parts of the input. Third question, we can say that correct option it's fourth one, because when computing the attention scores for a particular token, we hold its square vector fixed and compute dot products with the k vectors of all tokens to measure attention. Okay, if it's clear, we can move to fourth question. And here we will say that correct answers are this and this. The first one is incorrect because self-attention was originally designed for sequences. It can be applied to other types of data, like images or graphs, where relationships between elements matter. And second option and third one, second option, we can say that self-attention can capture long range dependencies and relationships between different parts of an image, so it can be applied to images effectually. And for the last option, we can say that self-attention can generalize beyond sequences and images, and it can be applied to more complex data like videos or graphs. So, and the question about positional encoding, we would say that the correct answer is the last one, because without positional encoding, the self-attention mechanism ignores the order of tokens. As a result, shuffling the input sequence along the time dimensions would produce the same result, as a mechanism cannot distinguish between different tokens positions. And the first one would be incorrect because it's not limited to text. However, without positional encoding, it loses the ability to model sequences. And second option, it's wrong because without positional coding, self-attention treats the input tokens as an ordered, meaning it wouldn't be able to different between a sequence that has been shuffled and one that hasn't. Here, we will talk about normalizer outputs of particular lawyer, and we would say that first two options are correct, because batch normalization works by computing the mean and standard deviation for each feature across the batch, normalizing the data feature-wise. And also, lawyer normalization normalizes the inputs based on the mean and standard deviation computed over all features for each samples. And the last one would be incorrect because min-max scaling is not typically used in the context of deep learning lawyers, especially for normalizing outputs of lawyers like batch norm or lawyer norm. It's more common in pre-processing steps. Okay, and the last question would be correct for first two options. For the first one, because positional encoding can generalize. No, it's here. It can generalize to sequences of arbitrary lengths, provided the positional encodings are designed for such flexibility. And in the first option, we can say that positional encoding is designed to incorporate information about the positions of tokens in a sequence which self-attention mechanism lack by default. In the third one option, we would say that positional encoding doesn't directly affect visualize. It affects how sequences are processed. And in the last one, we would say that it's not limited to the length of sequences seen during training, as the encodings are generalized to sequences of different lengths. Do you have any questions for the Google form test?
It's clear, thank you.
Okay, so today we will discuss transformer mechanism. I would say that it is main. Okay, if we will discuss natural language processing, for today is the main technology, which it's cutting edge and affects on others state-of-the-art approaches. I think it is important, and yeah, it's very important to discuss this architecture, because it would influence on a lot of other architectures. For example, we will discuss later large language models. As an example, we can discuss that ChatGPT or Claude or other chatbots that affects on people's life. Now it's made by large language models. And when we will discuss how does it works, we will say that it's one part of the transformer model. We'll discuss later why it is like that, and we will discuss on the lectures how does it works. But for now, we need just know that it is like that. So we will be building a transformer model from scratch using PyTorch today, and we'll focus on understanding each component in detail, covering the theory and discussing what is happening in the code step by step. Of course, now we can import all these parts of transformer model from libraries like transformers. In Hugging Face, we have a transformer library from which we can upload all the models and use it for fine-tuning. But I would say that in difficult projects, we need sometimes to switch layers of the transformer. We need sometimes train not all the layers, and do difficult tasks in which we can't just upload the model and work with extension one. So because of this, we will begin with the implementation from PyTorch, and let's begin with the multi-height attention class, which is heart of the attention mechanism in transformer. The attention mechanism allows the model to write the importance of different tokens in sequence relative to given query token. So here we just import libraries. Let's import them. And here we can see a formula of self-attention. We can see that we have multi-height attention. Let's discuss what it is and go in step by step of our code to understand why do we need all these input values, and why do we need query key metrics and others. So okay, here we pass insights to the class. This is dimensionality of the input embedding for each token. Each token in the sequence is represented by a vector of this size. We can see it in the comments of our class and function. So head size, each attention head will use this dimension for the key, query, and value vectors. The role of splitting into multiply heads allows the model to attend to different parts of the sequence. Number of heads defines the number of parallel attention heads. Multi-head attention enables the model to focus on different parts of the input sequence simultaneously. If num heads is 8, for example, the input is split into 8 different attention subspaces. And outsize, it's the dimensionality of output embeddings after processing the result of the attention mechanism are projected back into this size. Did you got what heads, what attention heads means? You can say that you didn't understand or that you understood, but can you tell me, please, summarization of this meaning?
No, can you repeat it, please, again?
Okay, I said that numbers of multi-head attention enable the model to focus on different parts. This means that it works, for example, like kernels in convolution networks. We have different kernels, and we can get different different hidden states or hidden features of the model, and understand more about our data in the latent space, I think. So multi-head attention enables model to do the same but in the different meaning. So if we have 8 heads of the attention, we will do self-attention 8 times, and we will do it in different ways. So because of all the heads in the attention layer, we will have different opinion of the model, what means how each tokens are influence on each other. Did you understand? Okay, I hope that.
Yeah.
Yes.
Yeah. Okay.
Sure.
So in the beginning of our lesson, I wanted to implement all the code just in the class, but now I see that we have 1 hour left, and I think it's yeah, we will discuss a little more, so maybe we will not going through our time breaks. And because of this, I will just copy paste different code blocks, and then I will say you what means each code block. So here, okay. One second. Okay, here we define the linear transformations that will project the input embeddings into key, query, and value matrices. These linear transformations take the input embedding for each token and project it in the respective spaces for attention. Query matrix, this one, key matrix and value matrix project the input into different spaces for key, query, and value for this one. All these sizes are proportional to the number of heads and head size. Here we see that this parameter influence on dimensional of our linear layers. And of the number of heads and head size. And the output layer, this one, is used to project the concatenated output of the multiply heads back to decrease out size. So in the summarization, we will make dot products of matrices and we will create these operations, and then we will create this operation on each head. And then we will concatenate all the heads in the one matrix, and then we will pass it to other layers. The intuition behind multiply heads, I will repeat it to be sure that you got on all the information, that the model can attend to various aspects of the sequence independently. For instance, in machine translation, one head could attend to verbs, while another focuses on nouns, giving the model a richer context to generate the output. Okay, here I will copy paste from this. This space. Okay, we'll just copy paste like this. Okay, next, let's look to the forward pass where the actional attention mechanism is computed. Here, this function processes the query key and value inputs. And it begins by reshaping the inputs into required size. Here we can see this. And for multi-head attention, and key operations include the linear transformations. The key query and value inputs are transformed via the linear layers defined earlier. I mean query matrix, key matrix, and others, this one. Each tensor is reshaped to dimensions. Here we can see that we reshape splits the input into num heads different subspaces. So we need to reshape it to batch size, num heads, and sequence length, and head size. Because of this, we here we have this in the comment on this line, but because of this, we transpose it through second and third dimension. Also, we have attention score calculation. Next step is computing the attention scores. Also, we can name it relevance. This is done by taking the dot product between the query and key matrices for each head. We saw it in the formula earlier. Here we create a dot product on this step. We compute it between the query and key matrices across all heads, divided by square of head size. Scale the scores to avoid large values, which could make the softmax function less effective. It's just normalization, and we can say that we do it because if we wouldn't do this, we will have large values. So then we can discuss why scale the dot product more deeper. When dimensions of key and query matrices are large, the dot product can result in very large values, making the softmax function produce very small gradients. And scaling by the square root of the head sizes solves this problem by ensuring more stable gradients. Also, we make on this step mask attention. In tasks like translation or text generation, we often need to prevent the model from attending to future tokens in the decoder. For that, we apply mask. And this step ensures that certain tokens, like future tokens in a sequence, are ignored by assigning them an attention score of negative infinity, effectively zeroing out their influence in the softmax operation. Then we get attention weights and output calculations. We can see it in these steps of our code. Here we get softmax. This function converts the attention scores into probabilities, ensuring the scores sum up to 1 across the sequence. We weighted this summarization. We then multiply these probabilities with the value matrix to obtain the output for each head. And for the last step, we concatenate the projection. The output from all heads are concatenated and project back to the desired output size using the outlier. Let's discuss the question why use weighted sums for all this process. By multiplying the attention weights with the value matrix, the model computes a weighted sum of the values where more relevant tokens, I mean those with higher attention scores, contribute more to the final output. Okay, is all the steps are clear for you right now? What we do in multi-head attention?
Yeah, I think we just went through the formula, right? It's everything according to the formula.
It's true, but it's very important to understand why we do this operation, why we transpose in these dimensionals, because usually it's crucial to understand this the steps, because okay, you will have it if you will go to interviews to different companies as a natural language processing engineer or maybe a machine learning engineer. And I know I met a lot this part of the code in my life. So I think it would be very convenient to you to understand all of this.
Yeah, I think you explained it really well. Thank you.
Okay.
May I just ask you to scroll a little bit back to the formula?
Yeah, of course.
Thank you. Okay, thank you.
Yeah, you will have this notebook, and I think I will do it. I will send this notebook and push in the GitHub repository as the empty one and the full this code. So you will be able to practice more, and also you will see the answers and all the right code operations. Okay,
thank you.
let's test. Okay, we will run this block, and then we will test a little bit multi-head encoder. So we see that mechanism multi-head attention mechanism using a sample input, it works, and we can go a little bit okay, going through all this test blocks, and it's necessary to discuss here. Okay, it's mask and the decoder. Yeah, we can see how to implement this mask. And I said you why we need this mask in the decoder layer, but right now it's very necessary to discuss positional encoding. Here we can see formula of positional encoding, and let's discuss why do we need this. Transformers don't have a built-in sense of token order, unlike recurrent networks. To give the model a sense of the position of tokens, in a sequence we use positional encoding. This is added to the input embeddings to inject information about token positions. Okay, let's go in through. Okay, I will copy paste calculation of positional encodings in tensor form, and then we will discuss what is going on. So why do we use sines and cosine? Here we have torch sin and torch cos. So by using these operations, these functions with different frequencies, the model can encode information about the relative positions of tokens. The intuition is that the periodic nature of these functions allows the model to easily compute distances between tokens based on the encoding. And here in the forward pass, the positional encodings are added to the input embeddings. The shape of these input embeddings is batch size. Here we have this batch size, sequence length, and embedding size. And the positional encoders are simply added element-wise to regular embeddings. Now we can test positional encoding, and we can see how does it works. .
Mhm.
Okay, here we pass max length and body size. So we take 1 second. Yeah, we take the input dimensions of shape, batch size, its batch size, sequence length, and embedding size. Then we add pre-computed positional encodings, which provide information about the position of each token in the sequence. And we can see the shape of the result. Then we can visualize what is going on in positional encodings. Here we can see distances of different tokens. It's just visualization of how does it connect with each others, and how can we understand what is going on in the deeps of this architecture. So this technique helps to understand positions of the tokens for transformer. And I think on this step, it's crucial for transformer to understand some grammar rules, some semantical differences between all the languages. How does it connect in linguistic way? And also, okay, we have yeah, I think we can say that for us, positional encoding and attention mechanism are the most important to understand where can we understand semantic of our text. So right now, okay, when it was just regular positional encoding, like here, just with simple formula, we could use only short length of our text, or just sequence. Let's talk about sequences, because it's no matter what does we provide in we can provide sound modality, or we can provide sometimes pictures for the transformers. It's no matter what, but we can say in the shortened way that we provide sequences on the input. And when we used this formula in the transformer, we could provide only around shorter than 500 tokens for the sequence. But if we will modify a little bit this function, I think we will discuss later how can we modify it. We can provide more tokens for our model, and it would work well. I mean, in simple way, we can't understand how does these tokens which distance they have if we will go in more than threshold that we understand in this simple way. But if we will modify it, we will be able to use long context of our sequentials. Okay, let's go in to the encoder block. Here we can see what we name encoder block in the transformer. We have covered multi-head attention and positional encoding. We can move to the encoder, which combines these two components along with a feed-forward network and a residual connection. An encoder block is the core unit of a transformer model designed to process the input sequence by applying attention, normalizing the output, and then passing it through a fully connected feed-forward network. Here we will define these visualized layers in the code. Here we have some text provided for embedding size and other values that we pass to the encoder. So here we have attention mechanism here. We apply multi-head attention using multi-head attention class we have already defined. This block calculates the attention bytes and produces the attended output for the input sequence. Then we have lower normalization. After attention, we apply a lower normalization to stabilize the training and improve converge speed. Normalization is crucial because it ensures that the scale of the output remains consistent. And also we have residual connection and dropout. A residual connection is added, meaning that we add the original input back to the output for the attention block. This helps it preserving the original signal and improving gradient flow during backpropagation. I think that you have already seen this before in computer vision. We had a lot of, I mean, in the machine learning area, we have a lot of computer vision models with residual connection, and it's widespread technique. So after that, dropout is applied to prevent overfitting by randomly zeroing some units during training. And then we have here a dropout. And then we have feed-forward lower. After normalization and dropout, the output passes through a feed-forward network. This feed-forward network consists of two layers, two linear layers. This ReLU activation function in between to get non-linear operations. This allows the model to learn non-linear transformations of data, further inching its ability to capture complex patterns. And also, finally, then we, after feed-forward network, we apply another residual connection and learn normalization to stabilize the outputs and ensure the model learns effectively. Okay. Here, I think you will have questions. Why do we use lower normalization, not batch normalization? It's interesting question, and I will try to explain you why we can't do like in convolution networks, but maybe you can guess by yourself if you have some interesting guesses why we do so. You can explain right now. If you haven't got, I can just explain by myself.
No guesses. Could you explain, please?
Okay, so if we would talk about transformers, we pass sequences in the input of architecture, and to get batch, we use some patterns. We seen this before when we implement recurrent networks. We used pet tokens to do matrix from the lines of sequences with different lengths, and when we hadn't more information in the sequence, but we had value which will be the maximum value of our context, we insert pet tokens in the end of the sequence, or if we had very long text, we just cut it, and we name it a truncation. So we create this matrix, and because that we have paddings in the end of some sequences, we can't do batch normalization because it would be not stable, and we will have errors when we will compute mean value and standard deviation, like in batch normalization approach. So because of this, we have lower normalization in the transformer, and also yeah, I think it's all the all discussions that I know about lower normalization and why do we use it. But it's very logic, and if you will, you can try to do batch normalization here, and you will not get good results because in the theoretical information, it's seems to be with some errors, and it's not the cleverest way to implement all the process. Okay, let's test transformer encoder. We will see our shapes of on this stage, what we get after encoder block of the transformer. Also, we can check for forward pass, and here one second. It's just, yeah, it's the same one. I doubled, I think, some code blocks of the notebook. So yeah, let's move to decoder part of computations. Okay, in the decoder layer, let's copy paste and then I will explain you what is going on. Okay, here we can see that we have a lot of similar blocks, but okay, we will discuss later what type of attention we have between two blocks. I will say you that it's very similar, but in the encoder layer, if we will use encoder block as a not with decoder as only one block in the architecture, we will see that on the output of the last layer, we can see that we will predict all the elements simultaneously. I mean, we will have here embedding spaces, and then we will predict from hidden spaces our outputs of the last layer. Here we will just add one linear layer and we'll predict something. Here, if we will use decoder layer, we will do after regression task. I mean that we will predict step by step each token, and on the output we will have linear block. Also, the difference between encoder block and decoder block, that here we can see all the context. I mean, context what was in the beginning. Then we stand on one step, and we can see what was in the beginning and what we have in the end of our sequence. But in the decoder layer, because we will predict after regression task, we can see only what was in the beginning. Because of this, we had masked multi-head attention to mask tokens with what we will have later, and we will predict it step by step. Okay, we can see what we implement mask. Okay. Okay, we need to run these code blocks. We have error when we use positional encoding. I try to find this line to understand what is going on. Why do we have error? And it's okay to have sometimes issues and mistakes. We don't have to scare about this. I don't see in the transformer decoder that we use this operation. Maybe we do something wrong. Okay, we use transformer decoder. And where did we implement it? I think that I paste something not in the right order, and because of this we have error right now. Okay, so let's move to transformer architecture, where we will combine all of the blocks with each other. We understood that encoder block, how does it look like, and let's look how to complete a transformer model and how does it structured. A full transformer is composed of multiply encoder and decoder layers, and each layer consists of blocks like the one we've just defined it. Here in this class, we can see encoder and decoder blocks. Transformer model consists of multiply encoder and decoder layers. Each layer applies multi-head attention and feed-forward operations. The encoder process the input sequence, while the encoder processes the input sequence, while the decoder generates the output sequence by attending to both the input and previously generated tokens. And this process is after-regressive in nature, as I said to you that decoder process is after-regressive. So when we use it with encoder block, it's after-regressive too. And we use one second. Also, we use here Okay, we don't use it. I will explain you that just each transformer encoder block is instated multiple times. And after passing through the decoder, the output is projected back to the vocabulary size using a final layer, and using final layer, and this converts the output into logits, which represent the model prediction for the next token in the sequence. Here, when we will discuss forward pass of the transformer, we see that the input going through its encoder and decoder then produces logits for each word in the vocabulary. So if we will explain more deeper what is going on in the last step, we will have a linear layer would be on the x dimensional, the same size as tokens in our vocabulary, and also this means that it would be the same with x dimensional of the input embedding layer, and we will have matrices of attention in these dimensions too. You could see this when we printed sizes of shapes of our layers. So you also can practice at home and print shapes of each layer when you will go through all the architecture. And I want to discuss you what will be on the output of transformer. We will have this here dimensional of size. We will have a size of all the tokens that we have in our tokenizer. Here would be probabilities after softmax, and we can predict then we will have a lot of probabilities, and also we want to choose one of them to predict next token. And in this case, we would have a lot of strategies how to choose one of this token. I don't know, maybe we will discuss it in some lessons after this lesson, but I will give you a short brief of strategies that we have. So we can use greedy search and choose token with a higher probability. Sometimes when we implement text generation, it doesn't work well, because we will not have emotional size of generation in generated text. Because of this, we have a lot of strategies. One of them is beam search. We can create a tree with beams that we set in the beginning. For example, it would be 3 beams, and we will have then tree with 3 different sentences in the prediction, and then we will summarize all the probabilities of these roads, and we will choose in the end of the higher probability in these generations. But it would work very slow, because in this case we will have to generate all three sequences, and we will have a computational complexity where we will have a number of tokens multiply on number of beams, and beams, and multiply on sequence length that we will generate. So we can understand that it would be a little bit heavy. Also, we can set threshold for probabilities in which we will choose. Its names top P. If you used ChatGPT via API or another instruments, I think you have seen this. It's we use it by set threshold of probabilities, and then for example it would be 0.9. Then we will choose in tokens that have higher probabilities than 0.9. Also, we have top K. It's parameter for set threshold for number of the tokens. For example, we would set 50 tokens, and in this case we will choose for the first step the highest 50 tokens with highest probability. Also, we have temperature in generation. Intuition of this parameter is emotional side of our model. If we will increase it to 1, we will have very emotional chatbot, or maybe whatever it would be. If we will set it to 0, it would action like we trained it on the train stage. Do you have some questions for the all information that I said on this lesson?
No questions so far.
Okay, nice. If you have no questions, I think we will finish right now, because we discussed all the information that we should discuss. But I think it would be a good practice to try implement a transformer by yourself, and print all the shapes of the operations of the matrices, because it will be in the future it will be convenient for you to do very hard projects on the work, and you will be able to change all the layers of initial model. And also, I didn't say that here we have not self-attention, we have cross-attention. on the stack of encoder and decoder layer, because it's okay. We don't change formula of our attention. We just we pass a query from another block, and because of this, we say that it's cross attention. Also, if we will implement multimodal multimodal approaches or models, it's widespread there to use cross attention to put another embeddings from other modality to another block. Okay, so I don't have I don't have any questions for you right now, and I don't have more information to discuss.
Okay, then. Thank you.
Thank you. Have a nice evening. Goodbye, guys.
Goodbye.
Thank you. Goodbye.